Well, thank you for staying this late with us. When I'm not bombarding you with emails, I deal with Apollo samples, and as the very well introduced topic in the previous block or complementary to it, I study the ages of Apollo samples. And in this particular case, I want to tell you a little bit about the Apollo 16. Is the microphone okay? I don't have the. Can you hear me? Yeah. Okay, so I want to tell you a little bit about the Apollo 16 samples. And this story is actually linked with the question that Caroline so well introduced today. We really need to know how old are the oldest basins on the moon. This helps us understand the early solar system bombardment history and the dynamics of the solar system. And we try really hard to date the oldest basins on the moon. Not only this helps us improve the chronology function and then further on establish the absolute ages of the surfaces, but it helps us understand whether there was the lunar cataclysm. We find more and more evidence not in support of this, or to say against this hypothesis. We tend to find some evidence about the oldest impacts that are older than 3.9 when the cataclysm or the late heavy bombardment supposedly happened. And this helps us interpret the expected exponential decay. That means that the crater frequency and the size decayed through time. But how does this actually work? Well, crater counting models, and as well as the models that try to trace distribution of impact melt across the lunar surface, do tell us that there should be a lot of material from the older impact basins. And this is what this map is supposed to highlight. So a lot of these big basins are older than 3.9, significantly older. However, when we look at the record in the samples, we definitely find most evidence for the Imbrium impact. The age of 3.9 to 2 million, so 3.92 billion years was very well established, and Imbrium is probably the basin for which we have the most exact age, or that the community has set on jointly. But there are some biases. Are we then biased when we look at all the samples because the Imbrium impact has affected all the samples that we look at? Or is the chronology or the chronometer that we are looking at very often we used argon back in the day, yielding us this age over and over again? The question is, are we overlooking the older ages? So the basins with the most debated ages are Serenitatis, Crisium, Nectaris. We think that we have the clue how old the SPA is. This is this age of 4.33, but we are only finding bits and pieces of information on that. So this is how I come to the Apollo 16. To find these old ages, we'll need to look at the dominantly anorthositic highlands, or the materials that are rich in magnesium sweet samples, some of the oldest rocks. And the Apollo 16 is very well suited for that. So how does it look like there on the Apollo 16 landing site? Well, the mission landed between North Ray and South Ray craters, and the geological map I'm presenting is also from Minster. The last one I have, so please correct me if it's been updated. Meanwhile, we have things to discuss. The mission landed in the Descartes highlands, but there are two pronounced formations in this region. One is the Cayley formation that is on the top, often linked to the Imbrium ejection, and underneath it is the Descartes material, slightly older, but also linked with the Imbrium ejection. So the question is how the samples reveal these ages. And wanting to understand the ages of these two formations, we focused on the samples that are linked to these two formations. One from the station 10, that is directly linked to the Cayley formation, and the other one from the station 11 that is actually brought to the surface by the North Ray crater, which was interpreted to have brought the Descartes formation onto the surface. So the objective of this study was to understand how old the breccias that are parts of these formations are, and what does it mean to actually date the breccia. You will see the ages can be quite complex. Doing this, we wanted to focus not on the argon-argon chronometer, but to understand in situ ages of the samples. And that means to look at the chronometers that we believe are more robust, like uranium lead, and in the accessory minerals, so individually dating each minerals. And this needs to be done because this is how the samples often look like. There is a centimeter scale on top, and these are thin sections analyzed for mineralogical composition. So these are ChemScan images of the two samples that we studied. And you can see that they're very, very complex. So as I mentioned, we focused on the anorthositic and MG suite rich samples like norites and troctolites. And you can see that these clasts, that there are clasts included in these samples. There are variable sizes. There are lithic clasts. There are so clasts of different rocks, but there are also mineral clasts inside. And the most dominant material is the very, very fine grained matrix material. So to look into the ages of these samples, one really needs to focus on different bits and pieces and to gather this information. So we focused on zirconium-rich minerals, zircon and bdelliite, and we focused on the phosphates as well by doing SIMS analysis of these minerals. We first need to locate these minerals in the sample, and you can see the scale here is 100 microns, so the grains are usually 10, 20 microns in size. And then you go to the secondary ion spectrometer that can analyze individual spot on these minerals. The spot size is about 10 micrometers, so it's very, very small. And I jump to the results immediately. So what are we looking at? So this is the KLA formation, the sample from the KLA formation, and I split the two chronometers, one for zircon and bdelliite and one for the phosphates. And what I show here is the weighted average age for the lead chronometer. And you see the ages on the y-axis. And this here is the age across all these points individually analyzed. And you see in this case of the KLA formation, we're both or all the accessory minerals are showing pretty much similar age, clustering around 4.22 billion years. There is no obvious difference between different clasts and whether the minerals are in the fragments or in the matrix. We find few grains that give us a hint of younger events at 3.9, which we believe is the reheating, or slightly older ages, which we're a little bit unsure of what they could present, but it's only 2 grains. So this is the top formation. If you look at the bottom formation, the Cartus formations, the Cartus formation, this is what we see. The ages that cluster around 4.2 are somewhat younger, but with a larger uncertainty, whereas the phosphates, most of them, or all that we analyzed, show the age that is indistinguishable from the Imbrium age. There is no sign of older ages in these phosphates. Again, no systematic difference between clasts and the matrix. And just a little bit of the niche for the people who do this. The lead ages I show are not all the ages we collected. We selected those that are concordant in the uranium lead systematics. That means 2 clocks on the uranium, 2 different uranium lead chronometers are giving us the same age. And this is the 4.22 age I showed in the case of the KLA. Also, we try to get rid of the samples for which we believe have terrestrial input. So we only focus on, for example, the red samples here that have the least common lead contribution. Whereas the ones that we are unsure of, we honestly say we are unsure about their age. We just see the hint of older or younger input. So to put this in the context, where do these ages fall? So this histogram here is the same summary of the data that I showed before, and you can see that they're differently color-coded. So pink, dark pink for zirconium, and then the others is salmon colors for phosphates. You can see that the zirconium rich phases show systematically older ages that cluster around 4.2, whereas, the phosphates are showing a wider range and tend to be younger. These phosphate ages often coincide with the argon-argon ages, and parts of the samples also coincide with the whole rock isochrone dating of the samples. So these are many different samples from the Apollo 16 sites, and we see this response or the age record in a number of them. Here I indicate the SPA, the 4.33 age that is not very present in the Apollo 16 samples, or the ones that we studied, but was found in other samples and at other sites. So to put this into the perspective, the 3.9 age, as I mentioned, was described or interpreted as the Imbrium age by the broader community so far. The other cluster that has found more consensus into the community is the 4.22 cluster that is recently interpreted across several sites to be of the Serenitatis age. The very old one at 4.33, very often linked to the SPA basin. And then the Crisium and the Nectaris is what's been recently suggested between 4.1 and 4.2, whereas the Crisium is less, melt is less expected at the Apollo landing site. And then with that, I summarize the conclusions that we are seeing variably recorded ages in different accessory minerals. So if you ask how old is a breccia, it's a very, very different or difficult answer to provide, because these breccia seem to record several events. And it's actually the question of which clock and which mineral you're asking. We saw the different clusters at 3.9, 4.2. In these lithologies. And now the question is where these ages come from, because the Cayley formation, the one on the top, was determined by the crater counting to be of the Imbrium age. So this ejecta that is derived by Imbrium to the landing site also contains a lot of material that is significantly older and definitely indicates the regolith mixing processes. I don't know if we really understand if these older ages have been mixed with the Imbrium material upon landing at the Apollo 16 site, or that's something that has happened at the Imbrium site before it landed at the Apollo 16. But yeah, this is to be discussed. And with that, I thank you for your attention.